Welcome back to Programming Fluency. This is section 11.3, Common Bug Patterns. Experienced C programmers do not just find bugs, they recognize them. In this video, you will build a mental catalog of the 5 most common C bugs, so you can diagnose most of them on site. Let's begin. Experienced C programmers do not just find bugs, they recognize them. After enough debugging, you start seeing the same 5 patterns over and over. A crash, probably a null pointer, garbled output, probably an uninitialized variable. In this video, you will build a mental catalog of the 5 most common C bugs, so you can diagnose most bugs within seconds of seeing the symptom. Let's get started. This is the plan for this video. First, the bug taxonomy, a tree that leads from a symptom to a likely cause. Next, off by 1 errors, a less than or equal to where you meant a less than, reading 1 past the end. Then uninitialized variables, garbage values that differ on every run. After that, segfaults, null and dangling pointer dereferences. Finally, undefined behavior and overflows, code that seems to work but has no guarantees. This is the key idea for this whole section. Pattern recognition turns debugging from a random search into a directed investigation. Instead of stepping through every line in GDB, you see the symptom, hypothesize the most likely cause, and go straight to the probable location. 5 patterns account for the vast majority of C bugs you will ever meet. Once you know them, most bugs become a lookup instead of a hunt. This figure is your debugging decision tree. When something goes wrong, the symptom falls into one of 3 categories, and you start at the top and follow the branch. When your program crashes, start with a segfault or a buffer overflow. When it produces wrong output, check for an off by 1 error or an uninitialized variable. When it hangs and runs forever, check your loop conditions. Each leaf of the tree is a named pattern with a signature in GDB, valgrind, or the compiler's warnings. Pattern 1, the off by 1 error, is the single most common bug in C. Look at this average function. The loop condition is I less than or equal to size. That is the bug. It should be I less than size. An array of n elements has valid indices 0 through n-1. Writing less than or equal to gives you n plus 1 iterations, so the loop reads array index m, 1 element past the end. On a stack array, this usually does not crash. It just reads garbage and adds it to the sum, giving wrong output. The fix is 1 character. Let's make the boundary concrete. For an array of size 5, the valid indices are 0, 1, 2, 3, 4. The condition I less than size visits exactly those 5 indices and stops. The condition I less than or equal to size visits 0 through 5, which reads index 5, 1 element past the end. So an off by 1 error is a loop that iterates 1 time too many or too few, or an index off by 1 position. The most common form is using less than or equal to instead of less than, which reads 1 element past the end. It is the single most frequent C bug pattern, so train your eye to spot the loop condition first. Pattern 2, uninitialized variables. In C, local variables are not automatically initialized. Look at this function. It declares int count with no equals 0, then increments count in the loop. But count starts with whatever bits happen to be at that stack location from a previous function call. Reading it is undefined behavior, so the result may differ from one run or machine to the next. The bug is insidious because the garbage might happen to be 0, giving the right answer on your laptop and a wrong answer on the grader's machine. The fix is simple. Write int count equals 0. Watch what happens when you run the buggy program twice. The first run prints 32,771. The second run prints 3. Different answers, same program, same input. That inconsistency across runs is the fingerprint of an uninitialized variable. Now run it under val grind. The uninitialized count is only detected when printf converts it for output. So the stack trace runs through vf printf and printf down to main, where count is passed in. An uninitialized variable is one that was declared but never assigned. Reading it is undefined behavior. Val grind's signature for it is the message. Conditional jump or move depends on uninitialized value. Whenever you see that message, you know the pattern immediately. Pattern 3, segfaults. A segmentation fault happens when your program accesses memory the operating system did not give it. Here find searches an array and returns a pointer to the match, or null if the value is not present. Main calls find looking for 99, which is not in the array, so find returns null. Then main dereferences result with star result without checking for null. Dereferencing a null pointer is undefined behavior. On most systems the program crashes with segmentation fault, core dumped. Core dump just means the operating system saved a memory snapshot for debugging, and you can ignore that part for now. To confirm in GDB, print result, and it shows 0x0, null. The fix is to check for null before dereferencing. Segfaults have 3 common causes and each has a diagnosis. First, a null pointer. In GDB, print the pointer and it shows 0x0. The fix is to check for null before dereferencing. Second, a dangling pointer to freed heap memory. Val grind reports a read inside a block that was freed. The fix is to never use a pointer after free, and to set it to null after freeing. Third, a dangling pointer to an expired stack frame. In GDB, the pointer shows an address in the stack range, but the function has already returned. The fix is to never return the address of a local variable. Pattern 4, undefined behavior, is the most treacherous concept in C. It means the C standard gives no defined result for an operation. The compiler and runtime can do anything, and the compiler is even allowed to assume it never happens and to optimize accordingly. Code can be correct on one system and wrong on another. Common forms are signed integer overflow, accessing an array out of bounds, and using a pointer after free. Watch out for the trap. Undefined behavior often appears to work. You test it, it gives correct results, and months later a compiler upgrade breaks it with no code changes. It works on my machine is not evidence that code is correct. One detector is the undefined behavior sanitizer, a compiler flag, -f sanitize equals undefined, that reports undefined behavior while the program runs. Pattern 5, buffer overflows. This happens when a program writes past the end of an array, overwriting adjacent memory. Look at greet. It has an 8-byte buffer called name, and it uses strcpy to copy the input in, with no length check. Calling greet with a 25-character name writes 26 bytes, including the null terminator, into an 8-byte buffer, overwriting 18 bytes of adjacent stack memory. Modern compilers insert a stack canary, a known value between the buffer and the return address, and check it before returning. When the overflow corrupts the canary, the runtime detects it and aborts with stack smashing detected. Buffer overflows are the most exploited vulnerability class in the history of computing. This figure shows why buffer overflows are so dangerous. On the stack, the buffer sits below the return address. When strcpy writes past the end of the buffer, it overwrites, in order, the stack canary, the saved frame pointer, and the return address. If the canary catches it, the program aborts safely. But without the canary, the overflow silently corrupts the return address, and when greet returns, it jumps to whatever address was written there, crashing, or in an attack, running code chosen by the attacker. This is how the 1988 Morris worm spread, and how the 2014 Heartbleed bug leaked data. The canary is a safety net, not a solution. This is the fix for the buffer overflow. Replace strcpy with strncpy and specify the maximum number of bytes. strncpy of name, input, size of name -1, copies at most 7 characters, leaving room for the null terminator. But there is a catch. strncpy does not add a null terminator if the source is too long, so the next line writes the terminator explicitly. So strncpy copies at most 7 characters, leaving room for the null terminator. The general rule: always prefer bounded functions strncpy, snprintf, and fgets over the unbounded ones strcpy, sprintf, and gets. This is the whole section as one checklist. Start with the symptom. Suspect the most likely pattern and reach for the right tool. A segfault means a null or dangling pointer, confirmed with GDB's backtrace and print. Wrong numerical output means an off by 1 in a loop, confirmed with a conditional breakpoint at the boundary iteration. A different result on each run means an uninitialized variable, confirmed with val grind. Works on my machine means undefined behavior, confirmed with the undefined behavior sanitizer. And stack smashing or an abort means a buffer overflow, confirmed by comparing the buffer size to the input length. That last tool, -f sanitize equals undefined, is a compiler flag you add when building. The program then reports undefined behavior as it runs. Treat it as a pointer for further study. GDB and val grind are the tools we drill here. 2 classic mistakes. First, less than or equal to instead of less than in loop bounds. If you write for I from 0 while I less than or equal to n, the loop runs n plus 1 times and reads array index n, 1 past the last valid index. The fix is to use less than n, a helpful mnemonic. The array size goes with less than, and the last valid index goes with less than or equal to. Second, using gets instead of fgets. The gets function has no length limit, so any input longer than the buffer overflows it. Gets is so dangerous it was removed from the C11 standard entirely. Always use fgets, with size of buffer as the second argument, which caps how many bytes are read. Let's recap. Most C bugs fall into 5 patterns, and recognizing them turns debugging into a lookup. Off by 1 errors show up as wrong numerical output, from a less than or equal to where you meant a less than. Uninitialized variables give a different result on each run, and val grinds uninitialized value message. Segfaults come from null or dangling pointers, diagnosed with backtrace and print. Undefined behavior is code that works but has no guarantees, detected with the undefined behavior sanitizer. And buffer overflows show up as stack smashing, prevented with bounded functions. Apply the checklist. Symptom, suspect the pattern, confirm with the right tool. Next, the best debugging strategy is to prevent bugs from ever reaching your code. In the next section, you will learn defensive programming.